As you'll see, I've slightly modified the title of the talk. So, how does this work? Okay. So, climate change has various effects, one of which is intense pulse disturbances, such as extreme heat events or extreme weather events. Potentially also tropical cyclones. There is some debate or controversy as to whether cyclones will increase in magnitude or frequency or otherwise under the effects of climate change. But regardless of what the effect of climate change is on cyclones, cyclones do have a massive impact on coral reefs. They potentially account for up to 50% of declines in live coral cover and potentially affect more reefs on the Great Barrier Reef than coral bleaching and disease combined. But as with all impacts or disturbances, cyclones have patchy impacts, and this is true for even the most severe cyclones. So I was conducting a study on the effects of Cyclone Yasi on exposed and sheltered reefs in the Palm Islands, which is on the central Great Barrier Reef, for anyone who doesn't know that, and it was close to the eye of Cyclone Yasi. So before the cyclone, on exposed and sheltered sites, live coral cover was between 20 and 30%. After the cyclone, perhaps unsurprisingly, on exposed sites, live coral cover was essentially reduced to zero. And specifically for Acropora, there were no live, reproductively mature Acroporas remaining. The only corals Acropora that remained were very small, immature juveniles. However, on sheltered reefs, coral cover and the size of Acropora, colony size distribution of Acropora was unchanged. I also looked at larval recruitment to artificial settlement tiles at exposed and sheltered sites before and after the cyclone. Before the cyclone, the numbers of larval recruit per tile were essentially the same on exposed and sheltered sites. Interestingly, after the cyclone, this didn't actually change very significantly. The numbers of Acropora recruits at exposed and sheltered sites were approximately the same. And this was despite the fact that there were absolutely no reproductively mature Acropora colonies at exposed sites. So clearly these reefs were being replenished by larval recruits from external sources. The sources are unknown at the moment, but they're clearly coming from somewhere else. And potentially for reefs that have completely lost reproductively mature corals, this is good news for their potential to recover. Obviously, lots of other things have to happen for them to recover, but without larval replenishment, it's not going to happen. So this information about larval exchange among reefs also fits with some of what we know about genetic connectivity. So I've genotyped over 2,500 Acropora tenuis colonies from 43 reefs for 10 microsatellite loci. And in 2011, Madeline Van Oppen published a paper for Acropora millipora based on 1,000 colonies from 20 reefs for 11 microsatellite loci. What's really interesting about these data is that there's really strong congruence in the genetic patterns between these two species. So this is just a very brief overview of these genetic patterns. But essentially, the northern and central Great Barrier reefs are essentially panmictic and are freely exchanging larval recruits, at least over periods of tens of years, not necessarily during every spawning season, but enough to remove any genetic distinctiveness between reefs. There's also a very strong genetic divide between northern and southern reefs, which may have a historical component. I'm not going to go into that. But interestingly, in the southern Great Barrier Reefs and in some of the central Great Barrier reefs, both Acropora tenuis and Acropora millipora are genetically distinct from other reefs. So on this particular figure, if I can get a mouse, the red indicates millipora and the yellow indicates tenuis. And everywhere where there's a circle, it means that there's a reef or a cluster of reefs that is genetically distinct from all the others. So in the southern Great Barrier Reef, which we already know is potentially facing more threats than other parts of the Great Barrier Reef and is already potentially in a more degraded state, is also potentially limited in its ability to recover from disturbance by reduced larval recruitment. So, thank you for coming to the talk. And I just particularly want to thank my collaborators, Madeleine Van Oppen and Betty Willis, for their assistance in this work. And lots of other people, particularly people who helped me in the field collecting corals and larval recruits. Thank you.